This is Miguel Pruneda from the Theory and Simulation group in ICN2. This video is going to be about the independent density functional theory as implemented in Siesta, and is part of the material of the advanced topics for the CECAM flagship school on first principle simulations of material with Siesta, which is organized with the support of the Max Center of Excellence. Okay, you are all familiar with static density functional theory, in which the electronic density and the external potential acting on the electrons are directly related. Now, if the external potential has some time dependence, the regeneralization of the theory is the time-dependent DFT, in which the density is also dependent on time. Now, if the external potential can be decomposed into a small time-dependent perturbation, then we can talk about the linear response approach to TDDFT, which is usually translated into the Casida formalism, right? So there is all this theory allows to obtain what is the response of the system to a small time-dependent potential, and allows to compute the change in the density as a function of time. Now, this is not what is implemented in Siesta. What we have in Siesta is the real-time evolution of the electronic density. So the parallelism goes is quite straightforward. We have this relationship between the potential and the density. Now it includes the time variable. The density is similarly to the Consham equation. Now they can be obtained from a Consham time-dependent wave functions, which are solution of the time-dependent Schrödinger-like equation. Okay. Now, once we solve this time-dependent Schrödinger equation or Consham equation, we obtain the coefficients. We obtain the wave functions. Now, from the wave functions, we obtain the density, and we obtain subsequently the potential. Now, the word of caution is that in general, the same way that in DFT, the exchange correlation potential is not completely known, in TDDFT, the exchange correlation potential must be approximated. And one of the most common approximation is known as the adiabatic approximation, in which the exchange correlation is determined from the instantaneous value of the density. Okay, then we have to solve this time-dependent Consham equation, and the way to do that is through the time evolution operator that gives you, from the knowledge of the wave function at a particular time, what is that evolution of the wave function at a later time, t plus delta t. Okay. And the functional form of this time evolution is basically determined by the Hamiltonian. Now, if you remember in Siesta, what we have is a linear combination of atomic orbitals expansion of the wave function, and at the end, this time-dependent equation translates into a time-dependent evolution for the coefficients of this expansion. If we assume that the basis orbitals are fixed in time, they are not changing, then the differential equation that we have to solve is basically determined by this operator, which is the inverse of the overlap matrix multiplied by the Hamiltonian. In the first implementation of this method in Siesta, the expression that was used for the time evolution was determined by the Crank-Nicolson operator, which has this complex form in which basically you have to take into account products of matrices and inverse of matrices. Now, also computationally this looks complex. It has a series of properties that make it very appropriate for this type of simulations. So, in particular, it preserves the orthonormality of the states. It's explicitly time reversal invariant, because the time reversal invariance is imposed during the derivation of this expression, and then it conserves the total energy. Of course, there are other propagators that are possible. and there are a number of papers in which people explore what kind of propagators are more convenient for time-dependent Schrödinger equation. In Siesta, a few of them have been tried, but probably the one that we think is rather efficient is the Crank-Nicolson, and that's the one that is implemented in the official version of Siesta. So as I said, in the first implementation of the method, that is in this reference, the idea was to apply it to obtain the optical properties of molecular systems. The idea is quite basic, and it was proposed by Javan and Berge in '96. You apply an electric field in a particular direction. As it's a molecular system, this is something the potential felt by the electrons is well defined. And then at time equals 0, you switch off the electric field and you follow the evolution of the density. And from the evolution of the density, you can compute also the time evolution of the induced polarization. Okay. Then by Fourier transforming this electric polarization, you can obtain the polarizability, and the imaginary part of the polarizability is related to the dipole strength function that itself is proportional to the photoabsorption cross-section, which is something that is directly observed in the experiments. Some additional notes. Take into account that we are talking about the dynamics of electrons, and the electrons are much lighter than the atoms, and they move 1,000 times faster. So the time step that we have to take in our simulation for our evolution is of the order of the attosecond. Okay. On the other hand, we have the Heisenberg principle that gives us what is the resolution that we could have for the energy, depending on what is the resolution that we have for the time. So if we want to have resolution of 1 electron volts, that means that our simulation, total simulation time has to be at least 4 femtoseconds. On the other hand, I have discussed before how to obtain the linear optical properties, but this approach is not limited to linear first order response. We could do a Taylor expansion of the polarization in the system and obtain higher order terms. Each of these terms will give us higher order susceptibilities. Okay. Then we also discuss how to do this for molecules. The problems with solids is that the position operator is ill-defined, and we have to change the formalism. The way to do it is to replace the electric potential, which is not periodic, by a vector potential, and that includes changes in the differential equation that we have to solve, the formalism. This, to my knowledge, has not been implemented in, well, at least it's not in the official version of Siesta. I don't know if there are other implementations around there where you could do these kind of things. Okay, so far we have assumed that the basis is not moving, but we could try to do non-adiabatic dynamics, and then the ions are going, the atoms are going to move, and the basis in Siesta is moving with the atoms. So instead of having this set of equations, now the wave function involves not only change in the coefficients, it also involves change in the orbitals, and the time derivative of this wave function has these two components. There is a new term that can be written as a function of the gradient of the orbital with respect to the atomic position multiplied by the velocity of that ion in the time-dependent differential equation. Now we have a new term that has to do with the change of the basis orbitals. This looks very much like a periphase, and it appears here as a covariant derivative, and there is a very interesting formalism that comes from these kind of expressions. And if you want more details, you can check in this paper here. Now, this adds complexity into the equations, and there are some tricks to circumvent these extra complexities, and one of them, the original one that was implemented years ago, is assuming that you can separate the evolution of the electrons and the nuclei. So you have you perform with a fixed atomic positions, hence with a fixed basis. You do the propagation of your electronic wave functions, and every certain number of steps you move the atoms. Now, the moving of the atoms means that the basis is changing, and the trick is to force an orthonormalization of the basis when this happens, and the way of doing this is similar to that. Okay, so you propagate your wave function, your coefficients to the next time. You normalize, you apply the loading orthonormalization with the old basis at the previous time, and then normalize again with the new basis in the new atomic coordinates. As I said, the moving basis means that you have to include new Poulet-like corrections in your equations. This load-in step that I mentioned is probably one of the most expensive operations that you have to do in the TDDFT, and it's not completely consistent with the formalism of the D matrix that was described in the work by Emilio Artacho. These effects are particularly important when your atoms are moving very fast. In this context, there are a few works, initiatives that are in progress right now. One is the replacement of the load-in formalism by other algorithms that would improve the computational cost. And the other is adding the corrections to the forces that come from this Poulet type of corrections due to the time dependence of the orbitals. These expressions are known. They have been shown in this paper by Todorov for a time-binding Hamiltonian, and they are now on the process of being implemented and tested in Siesta. Other important issues regarding to the propagation is what type of time evolution you use. So as I said, we were highlighting the quality of the Crank-Nicolson approach for this real-time evolution, but there are some tricks that could be applied. The first and easiest approach is just you basically take an extrapolation of the Hamiltonian, just a linear extrapolation to using the information of previous steps to guess what will be the value of the Hamiltonian in an advanced time, and then that improves the evolution of the coefficients. So this is an easy extrapolation, just a linear extrapolation. Something a little bit more sophisticated is to do an intermediate step propagation, where we use half time step. So we kind of do the propagation of the coefficients at a particular time, and from the advanced coefficients, we recalculate the Hamiltonian. So we have a Hamiltonian in an intermediate step, which then will be used to obtain the full propagation of the coefficients to the next time. And you can do this kind of tricks, extrapolation of the intermediate propagation, as many times as you want. You can divide the time interval in as many sub-steps as you wish, using this kind of methodology. This has consequence on the total energy and the conservation of the total energy. And here there is a comparison from a paper of the default Crank-Nicolson method. The total energy conservation is, as you see, is not well converged. But if you use the extrapolation or the two-step propagation, the quality of the energy conservation is very much improved. And the same in this other graph, which shows what is how far you can go in the improvement of the time steps. Okay. This methodology has been applied to study radiation damage in ions. Originally, it has been tested with metals and insulators, and there are quite a number of contributions in the literature. You can check a recent review showing this. But the idea is that you have a very fast atom moving through a host material, and you monitor what is the energy as a function of time. If you do this for relatively small velocities, then you recover an adiabatic movement, where you see the oscillations due to the profile that the atom is filling in the crystal of the host material. And as you increase the velocity, then the ion loses energy, and that energy is transferred to the electrons, and the electrons are heated, and that's why you see an increase in the energy. So with this methodology, you can estimate threshold velocities for the radiation, for the stopping power of an insulator. You can also it has been shown to provide reasonably good physical effects, like the Barkas effect. And in these simulations, you have to take into account that you have periodic boundary conditions. You are doing these simulations within a box, a simulation box, and your fast-moving atom can leave the cell, and when it leaves the cell, it enters in the other direction. So the size of the supercell is important. And you also have two transients effects, because you are starting with a configuration with static configuration, and then you start instantaneously moving the atom at very high speed. How do you use TDDFT in Siesta? The first thing, you have to specify in the input that the type of run for the molecular dynamic simulation is going to be TDED, time-dependent electronic density. You will have to do a first simulation where you initialize the wave function. So you have to specify Siesta in a first calculation to print into a file this wave function. That is the first run that you have to do. Then you perform the real time evolution simulation, where you evolve following the Crank-Nicolson algorithm the electronic functions, and every n steps you are going to move the atoms. Okay. The time step for the electronic evolution has to be defined with this variable, and remember this should be of the order of attoseconds, no more. Siesta is going to ignore the MD length time step if you have the TDED n steps. Okay, so the time step for the molecular dynamics, so moving atoms, is going to be the time step multiplied by the number of steps for the electrons. So if you are going to extract optical properties from molecules, in your first simulation you have to define in Siesta the strength of the electric field and the orientation of the electric field. Then it initializes the wave functions in the presence of electric field, and then in the next run that you are going to do with the time evolution, you have to switch off the electric field. Okay, so after the initialization, you should have a TDWF, so the wave functions stored into a file, and another file with the positions and velocity in case you are going to move the atoms. Okay. Then there are some options that you can specify for the solver for the evolution. These three, they have to do with this extrapolation approach that I described a few slides before. There are a few flags to determine what kind of information do you want to be saved into a file. In the case of the optical response, it's important that you write the dipole. Okay, you can also save the eigenvalues at each time step. Okay, and of course the total energy, which is it's a good idea to have always in your simulations, because it allows you to verify that your evolution is done properly. Okay, that your solution, your energy should be conserved. Other information that could be useful, you could tell Siesta to write the wave functions at the end of your simulation, so that if you want to restart your calculation, you can use that those wave functions and then continue with the propagation. And then you might be interested in saving the electronic density at every number of points in the evolution, okay, which is specified with this parameter. And I think that's all.